Okay, so what we're going to do is now jump into some mathematical, how do we do decision making? How do we make some mathematics out of this? Let me just tell you the next 4 lectures are going to arrive at an idea called false discovery rate, which again is something that's taught usually in the graduate curriculum, if at all. It's a researchy kind of topic. It's something you're going to understand, and I think you'll find kind of useful and beautiful. And when you go out in industry or you go to grad school, you will know about it and no one else will, and you'll feel real good about yourself and they'll be impressed. But particularly, I want to get to something called online false discovery rate, which is a very beautiful idea. I'm actually going to be able to give a proof that it works, and you will understand that proof. That's kind of also part of the ideas here. We're going to give you some simple, powerful ideas where there is an actual proof, and we're going to show that to you. And it doesn't require a huge amount of mathematical background, but just a little bit. And so hopefully that will incentivize you to learn just enough so that you can understand this. You'll start to see what kind of mathematics can eventually be done to support your thinking in fields like this. And so we're kind of carefully picking our examples which have such a kind of simple, beautiful proof. The famous mathematician Paul Erdős, hopefully some of you have heard of him. There was a book about him called The Man Who Only Loved Mathematics, I think. And he said that some proofs are the proofs from the book, that once you write them in the book, that's the only proof that will ever be. So we're aiming for a bit of that style in this class. All right, so we're going to go to kind of the simplest possible thought experiment, start thinking about decision making, and move towards aim in the direction of what's called false discovery rate. And I'm going to build that up, and it'll take me sort of 3 lectures to finally get there. And we'll do a little bit of kind of wandering along the way, but that's my goal. Okay, so we're going to start with the basics. We're going to go to the simplest possible situation where we have a decision to be made, and we're making decision making under uncertainty. If there was no uncertainty, this really wouldn't be so interesting for us. It wouldn't be data science. We have to have some uncertainty. All right, so we're going to suppose that there's a reality is in one of 2 states, which we denote as a 0 or 1. What is reality? Well, it's whatever you want it to be in the problem you're modeling. For concreteness, let's think about this epidemic. Reality is that some particular person has the disease or does not have the disease. Okay, so 0 could be they don't have coronavirus, they've not been exposed, and 1 is they've been exposed. The virus lives inside their body. And even that's a vague kind of concept, how much does it live inside the body? How do I get it out, and all those things. But let's assume it's a 1 or a 0. So we're not going to observe this actual state. Obviously, we can't just observe it. We collect data, and particularly we do a test. These swab tests that you're seeing people put in their nose nowadays. I haven't had that happen to me yet, but maybe some of you have, and probably all of us will in the next year. Okay, so we observe data. Now that data obviously is going to be different if you have the coronavirus versus you don't. Okay, so we're going to have a conditional distribution, conditioning on a 0, coronavirus, no coronavirus, what's the data look like? Or versus conditioning on 1, you do have the coronavirus, what's the result of the swab look like? If those distributions were the same, we couldn't do any testing. So hopefully those distributions differ. And we'll need to talk about quantifying that. All right, so now we're going to make a decision based on the data, which we denote as a 0, 1. And so it's going to kind of look at those the data, aware of the 2 distributions that are involved, and try to kind of do an inverse problem of figure out what must have been the state of nature that gave rise to that data. Statistics is fundamentally an inverse problem. It's observing some data and trying to going back to the state of nature that gave rise to that data. It's an inverse problem. In fact, historically, statistics arose really in the 1700s. Probability already existed as a field. There was no statistics, and it arose, and it was first called inverse probability. It wasn't called statistics until the 1800s. Okay, so that's our little setup here. We're going to have 1, 0, 1, 0. So now we can draw a little simple table. Reality is going to be on the left-hand side for me, 0 and 1. So you have the virus or you don't. Okay, so reality will be on the left-hand side. And then the decision is something you do as an agent, someone does. That's going to be in the columns. Okay, and so we're going to either decide a 0 or a 1. And now we can start populating this table with some standard terminology. And you need to memorize this. You probably already have, but let's just really get clear on it. Okay, if reality was 0, all right, that's where you should not make a discovery. That's another language we're going to be using. You should not say I found something, because there's nothing to find. Reality is that you don't have the coronavirus. You should not be saying you have the coronavirus. And so if your decision is a 0, that's called a true negative. Negative refers to reality, the state of reality. You should be saying negative. You did say negative, so it's a true negative. In that same row, if reality was 0 and you said 1, that's a false positive. And you've all heard about false positives a lot. They're really, really important in real life. Too many false positives and systems don't work. All right? But there also is a counterpart. There's a false negative, meaning reality was a 1 and you falsely said 0. Okay? It's a false negative. Okay? In that same row, there is a true positive, which you should have said 1 and you did. It was the right answer to say positive. All right, and now you can sort of see in this little table, the green stuff is the good places to be. True negative or true positive are both good things to do, and red is bad. So roughly speaking, we like to be most of our decisions in the green and a few of them in the red. All right. But how do we make that more concrete? And is there more than one way to do that, or is there only one way to do that? You know, what are the advantages and disadvantages? And if you start thinking about particular problems, you'll start to see that it can't be just one way to do it. And it really starts to matter about the particular problem. So I'm not going to go through these, but I would actually encourage you to step through them yourself later and think about, in each one of these examples, what is a false positive? What is a false negative? And how desirable are the true positives and the true negatives? Okay? So just kind of briefly say something about it, you know, medical. What if you don't have the disease and you have a false positive? Okay, that means you don't have the disease, but I said that you have the disease. That's a false positive. How serious is that? Yeah, well, it's pretty annoying, right? It scares people that, you know, you have, you're told you have cancer and you actually don't, but you're told you are. That's not very good. That's a false positive. And false positives tend to be annoying. They also tend to make people not pay attention anymore after too many false positives. All right, but now think about the false negative situation, which is where you have the disease and the test said you didn't. That's the other kind of error. Now that's arguably in the medical domain even more serious, right? You have cancer and I just told you you didn't. That's pretty serious. All right, and so we might want to boost the false negatives somehow relative to the false positives, but they're both serious. And, you know, true positives and true negatives, you might argue about which is more important. And I kind of want you to go through each one of these here. It really would be a good exercise for you. Think about commerce, where like you're trying to detect fraud versus no fraud, right? How much does it annoy people to be told it's a fraud when it's not? How much would you like to be generous to customers so they're not annoyed? And, you know, and how much do you not worry about losing money and so on? Or think about, a classical hypothesis test situation. Is there a Higgs boson or is there a not? Okay, that's a question that people ask. That's something they're still kind of asking. The truth is that there is or there isn't, and you decided there is or there isn't. Pretty big decision. And you should think now about the consequences of if there is no Higgs boson and I said there was, how bad is that? That's a false positive. Versus there was, no Higgs boson and I said, there is a Higgs boson and I said there wasn't. How serious is that? A little bit different than the medical example. Self-driving car, is there a pedestrian there? Is there not? Do I turn to avoid the pedestrian or not? I think that's pretty interesting. Oil well drilling is an interesting example, right? If you drill an oil well, it'll cost you money to do that. If there's no oil there and you drilled anyway, that's a false positive. That's bad, but how bad is it relative to a false negative where you didn't drill there, you just lost an opportunity? Okay, so great examples to be thinking about, and I hope you'll kind of think about some of your own. Okay, now that was just kind of a little picture of here's a decision-making problem one time. In real life, it's really not just, it's pretty rare there's just kind of one-time decision. There's usually many decisions that are somehow grouped together. And maybe it's a group of people, or maybe it's one person making the decision over and over again. But we often will have, data that's not just one data point. We'll have lots of data. And so we'll start to now move towards a set of related decisions and have not just one decision, but a decision rule. Okay, we're going to have an algorithm that makes decisions, and we want to evaluate the algorithm. And we're going to do it not just on one problem, but a whole set of related problems. So statistics is often the field that decides how to help you evaluate systems, how to evaluate a decision rule. Is it a good decision rule or bad? Well, it kind of depends on your criteria. And statistics is the field of evaluation often. All right. So we might repeatedly accept the null or accept the alternative, or we might have classification decisions where we repeatedly say that's a fraud or that's not a fraud, and we'll do it again and again and again. And we worry about the behavior of this system over an aggregate or over the next data point data set. So now instead of just having one decision in our table, we're going to have a number of decisions, and I'm going to denote them with n. So n sub 0, 0 is the number of times you made you said 0 when you should have said 0. Okay? So true, negative. And n 0, 1, that's the number of false positives. These are now counts in this table, and they add up to the total number of counts, capital N. Okay, and so now to be more statistical, we're going to talk about uncertainties. We're going to talk about rates and probabilities. So first of all, every time we get a data set, those numbers will be different, right? Different people, different situation, different context. So those numbers n 0, 0, n 0, 1, and all that, those are going to be random variables for us. We're going to bring in probability language, okay? And we'll have to be really clear on what our randomness is here. It'll be a little different if we're thinking in a Bayesian way versus a frequentist way. And whether we're thinking of the state of reality as either fixed or random, we're going to have to talk about this. All right, so now it's going to be very important for us to distinguish between the row-wise rates and the column-wise rates. All right, and this is really starts to get important. People get confused all the time about this. And when I say people, it's not so much students. It's like people on the news. It's like people in newspapers. It's like, all the time, you see this all the time, that someone's making a statement about some rate, some ratio of the number of people, I'm going to mess this up a little bit, but I'll do maybe a better job next time. But it just occurs to me, it's an important one, which is, so the probability that you are killed or you're shot by the police if you're black versus white, that's a pretty important number to get your hands on, right? It's one you could argue about and all that, but really we should kind of get some data. And there was a couple of months ago an article in the Proceedings of the National Academy of Sciences that was picked up by the Wall Street Journal and so on and so forth. And it claimed that there's no difference between blacks and whites in terms of probability of being shot by the police. But what it turned out was they got the rows and the columns switched. That they were talking about if you were actually stopped by the police, what's the probability of being shot? And it turned out to be similar. Okay, but the real quantity that we care about is the opposite one, right? What's the probability of if you're black that you're shot by police, right? And if you know Bayes' theorem, it's switching from rows to columns. And of course, if you switch like that, the number gets much, much higher. If you're black, you are more likely to be shot because you're more likely to be picked up by the police, all right? And then even if the probability is the same of being shot at that moment, which is arguable, but you can look at data, it's a very different question. And so that was picked up in the Proceedings of the National Academy of Sciences. It was picked up in the Wall Street Journal, and obviously it was picked up on Fox News, and it was wrong, and it was just dead wrong. And it was this problem right here that we're about ready to discuss. Okay, so row-wise rates are kind of the classical statistical perspective, frequentist perspective typically. And what it does is it says, what if the state of reality is 1? What's the number of times you make decision 0 versus decision 1? This is called a sensitivity if you take that ratio. So I take the number of times I said 1 when I should have, that's good, that's a true positive, that's n11, and I divide that by the total number of times that reality was 1. All right, so if I'm doing coronavirus stuff here, I'm looking at the total number of people who actually have the coronavirus, okay, and I did some testing, and on some of them I said, yeah, you got the coronavirus, and on some of them I didn't.
You don't.
Obviously, I want to more often than not have that I said you had the coronavirus, because you do. And so I want a high sensitivity. I want N11 to be really, really large relative to the total number of times of people I looked at who had the coronavirus. Okay, so you can measure a test by its sensitivity by just doing some, you just take the test and you try it against, get a whole bunch of people with coronavirus, try it and see what fraction you have. And so most of the tests for things like coronavirus are like in the 80 to 90% range. On other problems, you get sensitivities which are higher or lower, but that's a typical number. All right, so this is often sometimes called the recall in other literatures. It's also sometimes the true positive rate, or some in the classical statistical literature, it's called the power. These are exactly the same concept, okay? No different. You can use either one, any of them you most like, all right? But they are a row-wise, the second row in our table. The first row in our table, if we take that same fraction, it's called the specificity, all right? This is the number of cases where you're 0. How many times did you make the right decision there? You said 0. So in the coronavirus case, this is people who don't have the coronavirus. How many times did you say, no, you don't have the coronavirus? Okay, So a test could be really highly sensitive if you just say to everybody has the coronavirus. Okay, that would be the lower row of the table. You just say, oh, yeah, everybody's got the coronavirus. So my fraction will be 1. I'm always detecting it. But the problem is I'm detecting it all the time. I'm not specific. So the first row tells you about whether you're specific or not. Do you not detect it when you should not? So you don't have N01 being large, okay? So ideally we'd have both of these, and I hope you can sort of understand there's gonna be a trade-off between these two. All right, so we're kind of now in kind of classical statistics land and signal processing and other land where we talk about these trade-offs and we talk about these row rates. Another names for these are the type 1 and type 2 errors. You know, you've all heard about these. We're gonna focus on something different. We're not gonna focus on these row rise rates. And I'm gonna try to get that home to you in this lecture and in the beginning of next lecture. So other names for specificity are true negative rate selectivity. By the way, there are Wikipedia pages on that. If you type Wikipedia specificity, you'll find a whole page devoted to all of these synonyms and tries to explain it. So these row-wise rates are conditional probabilities, or they're estimates of conditional probabilities. So for example, the second row, sensitivity, is an approximation of the probability that if when reality is 1, you made a decision equal to 1. Okay? So it's a conditional probability conditioning on reality. That's a frequentist kind of thing to do, is condition on the truth, which you don't know, and say something about the probability of an outcome, a decision. Okay? So these are not dependent on what's called the prevalence, which is the number, the probabilities of the two states of reality. We're just saying we're looking at all the people who have coronavirus, and we're saying if you have coronavirus, what's the probability that we detect it? That's your sensitivity. It has nothing to do with the number of people who have coronavirus. It's just if you have coronavirus, what's the probability we detect it?
Mike, you have there's a question from David Liu, which is what's the reason for the names that are given to sensitivity and specificity?
Okay, thanks. Yep. So I tried to say this, and let me just say it again. But again, you might want to look at this Wikipedia page and just have it, something you look at from time to time. These words take everybody about 5 or 10 years to get used to actually remember them. And so I'll do it again, but it'll take you some time. Okay, sensitivity is if something bad is happening, like you have coronavirus, what's the probability that the test detects that? How sensitive are you to the presence of the bad thing? Okay, if the test is geared to detect coronavirus, is it sensitive? Does it detect it when you have it? So that's the probability the decision is equal to a 1 when reality is equal to 1. That's what I've written on this slide. That's the second row of our table. So sensitivity. Okay. Now, again, if you're just detecting it all the time, every time someone gives you a test, you say, yeah, they got coronavirus, yeah. You're going to have a high sensitivity because you're saying it yes all the time, and therefore every time someone has it, you say yes. Okay, the problem there is you're not being specific. For other people who don't have it, you're saying you have it. Those are false positives. And so you're not being specific that I'm only saying yes when you actually have the coronavirus. So specificity is that other row. It's the probability that when you shouldn't say you have the coronavirus, that you're actually not saying it. Okay, you don't have a false positive there. You're being specific. You're only saying you have it when you do. All right, so I hopefully, especially since this has been recorded, you can listen to that again, and hopefully that'll do it. And hopefully I got it right, by the way. I've been doing this for a lot of years, and I still can sometimes flip these things around. Also, I very rarely use the terminology of type 1, type 2 errors, because those are okay. So let me then move on a little bit. And indeed, here's in those classical definitions of type 1 and type 2 error, those are 1 minus specificity and 1 minus sensitivity. But I would just encourage you to ignore that. Pick whatever word you prefer, but maybe specificity and sensitivity, they at least have some semantics. All right, so we'd like to have both of them being high. But here is a so-called ROC curve, which tries to plot the two together and shows that there's a trade-off. Okay, so on the x-axis here is the false positive rate. Okay, and remember that's 1 minus the specificity. So this is the top row of my diagram. Okay, and so I want to have a false positive rate which is near 0. I want to be at the bottom. Okay, on the left side of the x-axis. Okay, I would have plotted this, reversed it, and plotted sensitivity and specificity, but this is the classical way it was done. So I got to teach it this way. All right. And the y-axis here is the true positive rate. That's the second row of the table. That's the sensitivity. Okay. And so it is exactly the sensitivity. True positive rate is the sensitivity. Okay. So you can flip the x-axis and you would have the specificity and sensitivity. All right. So here's an important slide. This is the first new one. I've just written down Bayes' theorem, which you hopefully know from Data 140 or many other places. It's a very important theorem. It will help you in your life as well as in your academic career, because lots of decisions you have to make, it might be a good idea to actually write down some of the probabilities with this theorem, and especially make sure you get the prevalence right. If you just had a bad result at the doctor's office, some test you did came out bad, you should think about what's the prevalence of something, that bad thing happening. How probable really did I have before I even looked at the test values? So we'll be talking more about that kind of thing as well as we go. Anyway, here we have the probability of reality being in one state or the other, given a decision. Okay, so I'd call this Bayesian because it's based on the decision, which is based on the data. So really, we're conditioning on the data. And that's a Bayesian thing to do. Conditional on the data. What's the probability of reality? In other words, what's probably the hypothesis is true or that it's false? Okay, so we'll be talking more about Bayesian, but I think of this as a Bayesian quantity. All right, and I think I had a slide in here that seems to have disappeared, but maybe it'll come back in a moment here. Okay, so let's now go to the column-wise thing. This again is a slide from last time. All right, this to me is now going to be more important for this class than the row-wise quantity. So let's pay attention, especially here. This is the most important one to me for this class. It's called the false discovery proportion. Of all the times that you made a discovery, i.e. you made the decision equals 1, you said, person has the coronavirus, or this is a fraudulent transaction, or whatever. Of all of those times, what fraction of those were actually errors? Okay, what fraction of those were false discoveries among the total number of discoveries? So N01 is a false discovery. N01 plus N11 is the total number of discoveries you made. All right, so already I want to give a hint about why this is kind of a neat and a better way to think. N01 plus N11 in the denominator, that's the total number of discoveries, total number of times you said 1. That's something you can know because you saw how many discoveries you made. You can just count them up. Whereas in the row-wise quantities, those things were like the total number of times reality was equal to 1. Well, you don't know that because that's the whole point. You're not the supreme being. You don't know what the truth is out there in the world. So the denominator is unknowable, but here it's knowable. Okay, now these things are ratios, and for the same reason as we talked about before, you could think about them as estimates of conditional probabilities. They are dependent on the prevalence, and that's going to become clear on the next slide, so let me not belabor that here. And we're going to be using Bayes' theorem to kind of make this all clear, and in fact, this kind of way of thinking is going to be more Bayesian. You're not Bayesian just because you use Bayes' theorem. It's really because you condition on the data and you're willing to talk about the probability that the null hypothesis is true. That's a Bayesian thing to be willing to do. And you're using Bayes' theorem to support that argument. Okay, so the next few slides, I'm going to be doing a little bit more math. And so instead of writing out words like reality and decision, that's too long. I'm going to use the letter H to denote reality. So think hypothesis, and D will denote the decision. Okay, so here's Bayes' theorem again, now a little more mathy looking. And so I'm taking in particular the case where the decision was a 1, and I'm looking at the probability that the hypothesis was a 0. Okay, so this is an error, and it's a probability of an error. You thought that reality was 1. In fact, reality was 0. With Bayes' theorem, then we can write that out, just like I did before. So it's the probability that D equals 1, given that H is equal to 0. That's a false positive probability right there. That first term in the numerator there is the probability of a false positive. Probability that you said 1 when you should have said 0. Okay, so that false positive probability is embedded in this false discovery probability, which is what the left-hand side is here. All right, now we multiply that by the probability that H equals 0, and then we divide by the probability that D equals 1. Okay, just Bayes' theorem written out now with particular cases of ones and zeros. All right, now a couple of points about that. First of all, on the right-hand side, the probability that D equals 1 given H equals 0, again, that's the false positive probability. Okay, that's a row-wise quantity because we're conditioning on H equals 0, right? We're conditioning on being in the first row of the table. And we're saying, what's the probability that you're in the upper right-hand corner given that you were in the first row, right? That's on the right-hand side of our equation. And then we're multiplying and dividing by something. And on the left-hand side, we're getting a column-wise quantity. Okay, the probability that H equals 0, all right, given that D equals 1. That says that you're in the first column, sorry, the second column, D equals 1 column, all right? And you want to know, given that you're in that column, what's the probability that you're in the upper right-hand corner, okay? The probability that you're making a false positive, but now relative to all those cases where you made a positive decision. Very different than the false positive relative to all those number of cases where the null hypothesis was false, or sorry, true, when H is equal to 0, okay? We're looking down a column instead of across a row. In both cases, the numerator, though, is that upper right-hand corner in the table. All right, so that's the first point, which is Bayes' theorem in general relates one conditional probability to another, flips things around. Or if these, think about these little tables, it's flipping the rows and the columns. All right, the other point to make is that we definitely see the prevalence sitting here on the right-hand side. The prevalence, now to be really precise about it, we're going to be defining that to be the probability that H equals 1. Okay, so if H is, for example, that you have the coronavirus, then the probability that H equals 1 is the probability of people having the coronavirus. That's exactly the prevalence of the disease, okay? And so if I know probability H equals 1, then by just subtracting from 1, I get the probability H equals 0, so it's the same thing. And probability that H equals 0 appears up in my equation there in the numerator. So I can clearly see that this false discovery probability, the probability H equals 0 given D equals 1 on the left-hand side, it depends on probability H equals 0. Okay, it's built in there, all right? And I think that's a good thing for making good decisions. But whether it's good or bad, it's just a fact of life. All right, now let's do a further calculation here. This is the most math I'll do today, although I wouldn't call this math, it's like arithmetic. But I'm gonna now just pursue that little Bayes' theorem thing a little bit further. So the first line is, I just copied it from the previous slide, okay? The second line, all I've done is replace P of H equals 0 with a new symbol, pi 0, just so I can simplify my life, okay? The third line, I've used what's called the theorem of total probability. Probability that D equals 1 is probability that D equals 1 given H equals 0 times pi 0, that's the probability H equals 0, plus the probability that D equals 1 given H equals 1 times the probability H equals 1, which is 1 minus pi 0, okay? This should all be super familiar to you. If it's not, then Professor Adhikari will be mad at you, and maybe me too, but certainly at you. But I know it's really clear to all of you, so no problem. But if it's not, please just go through this really, really slowly on your own, okay? Now, the next step, what I've done is I've divided the numerator and the denominator by the numerator, okay? We're going to be doing this several times in the class. Particularly when we get to logistic regression, this is going to be an important step. So I've got 1 over 1 plus, and then that second term there is going to get divided by the numerator, all right? So I've got probability equals 1 given H equals 1 divided by probability equals 1 given H equals 0. Then I've got 1 minus pi 0 divided by pi 0. Okay, so this is really important little expression here. This tells me that this Bayesian posterior probability, the probability of a false discovery, is just 1 over 1 plus something, right? And that something there, the first expression there, that probabilities of D is equal to 1 under these two cases, that's called a likelihood ratio, okay? It's a likelihood of D under hypothesis equals 1 versus the likelihood of the data under H equals 0. Okay, so that's a likelihood ratio. The 1 minus pi 0 over pi 0, that's a prior ratio. Okay, that's a prior ratio. All right, so let's look at a couple of consequences of this. All right, first of all, we can see really the prevalence has a major effect on the probability of an error. So let me go back here. 1 minus pi 0 over pi 0, that number can range from 0 to infinity. All right, so that can have a huge effect. Just how many, what's the prevalence? It's going to have a huge effect. Let's be really quantitative about that. Let's look at our likelihood ratio, and let's suppose there that probability d equals 1 given h equals 1 is 0.8. What is probability d equals 1 given h equals 1? If I were in the classroom right now, I'd pause for a second and wait for everyone in the first 2 or 3 rows where the eager people tend to sit to yell at the answer. Okay, so that's a true positive. All right, the truth is that is 1, and I should be saying a 1. So that's probability that happens. So let's say it's 0.8. It's also the sensitivity. Okay, so we got a sensitivity of 0.8, which is pretty good. It's actually kind of typical for things like coronavirus testing. Is that, the situations where you should find the coronavirus, how sensitive are you with your test to finding it? Well, 80% of the time you find it. That's not too bad as a sensitivity. All right. The other number is a false positive probability, or 1 minus the specificity. That's the probability d equals 1 given h equals 0. So that's your false positives there. Okay. You should have said false because h equals 0, but you said 1, d equals 1. And let's suppose your false probability is 0.05. So that's a typical value as well. That your specificity is 1 minus that, in other words, 95% specificity. So it's a pretty good test. All right, now if we take our likelihood ratio, that 0.8 divided by that 0.05, if I did my math right, that's a ratio of 16 to 1. So if you go back to my formula and Bayes' theorem there, I got 1 over 1 plus 16 times my prior ratio. Now, if my prior ratio was, suppose that pi 0 was 1/2, then I'm going to have 1/2 divided by 1/2. That's just going to go away. I'm going to have 1 over 1 plus 16. Okay, so 1 over 17. So a really small number. So the error here, the false discovery error, is nearly 0. That's pretty good. I got a good enough sensitivity and specificity that I'm able to drive the false discovery error now near 0. So it is good to have a good sensitivity and specificity, right? But it's not everything, and in fact, it can be illusory. So now let's look at a different case. Still, let's have 16 to 1 as our likelihood ratio. But now let's suppose the prevalence isn't 0.5. Like it's not the half the people have the coronavirus. Someday that may happen, but it hadn't happened yet. So it may be more like a prevalence of 1 in 1,000. And in things like epidemiology or fraud or many other cases, this is common. 1 in 1,000 or 1 in 100,000 or something is kind of the number of bad things out there. Okay, so the prevalence is really, really small. Okay, so that means 1 minus pi 0, which is the prevalence, divided by pi 0, which is 1 minus that, is tiny. Okay, it's really, really small. All right, so when you're multiplying in this formula here, that really tiny number by your 16, it kills the 16, and you get 1 over 1, more or less, plus a little bit. So 1 over 1 is getting very, very close to 1. So your probability of making an error of one of these false positive errors is going to 1. It's really, really terrible. Okay, and this is a serious problem, and not enough people out there appreciate this. Again, you will see errors in the newspapers. You'll see errors certainly among politicians, but not only, making this kind of error, that when things have really small prevalence out there, even though you've got a test that supposedly has been rated at high sensitivity and specificity, and therefore is a great test, it can give you nonsense. It can give you really, really bad false discovery rates. Now, when I say nonsense, I mean really with respect to this false discovery proportion, this probability of making, on the cases that you made a discovery, what fraction of those were actually bad discoveries. And I'm going to argue that's a good thing to think about in lots and lots of problems. That you've made some discoveries, there's a bag of discoveries you've made, those are the things that all the attention is going to be focused on, and you want to know in that bag, what fraction of them are bad discoveries. The probability that h equals 0, given that you said that d is equal to 1. And we're saying that that number can really be bad, even though the sensitivity and specificity are high. Okay, so that's kind of one of the main points I wanted to start to make. Hopefully that's starting to become clear to you that thinking about these column-wise things, it's not the traditional way that you learned in statistics or many other fields. In fact, epidemiology, you'll learn about sensitivity and specificity, and then maybe you'll learn a little bit more about these column-wise quantities, but not so obvious. In many fields, you don't learn about it at all. But for you guys, this is going to be our starting place.
I have a quick question, Professor. Is the prevalence the probability that H is 0 or H is 1?
H equals 1. That's just my arbitrary decision. That's just more accords with kind of, I'm kind of using epidemiology as my running example here. And prevalence is the probability that H equals 1, where H means you've got the disease. And so prevalence of bad loans would be another case. You know, someone submits a loan application and either they intend to pay off the loan or they don't. So let's let H equals 1 mean that it's a bad loan and we want to find those. And so the prevalence of bad loans out there would be the thing that you would be trying to, worry about. All right, but type 1 error is the thing I was calling 0.05 on the previous slides, probability of a false positive. And I was saying that in a case where you have a very, very low prevalence, you've only got 100 non-nulls, and you've got most of these hypotheses being null, 9,900 true nulls. Here you have a very small prevalence of the non-nulls, the things you're trying to discover, all right, out of all 10,000. And our probability of a false positive is 0.05. All right, so in all those cases where we should be saying null, all 9,900, we multiply by 0.05, we find only that 495 of them, a very small fraction of them, we made a discovery when we shouldn't have. Okay, that looks good. And similarly for the second branch here, that's the sensitivity or power. And so we're saying that we have 80%, 0.8. So of those 100 discoveries we should make, we discovered 80 most of the time. But now if you look at, those are the row-wise column, row-wise errors. If you now look at the column-wise one, which is that you ask of all the discoveries you made, which are 495 plus 80, 575, how many of them were false? And the supreme being or the oracle, whatever, knows that 495 were false out of the 575. And so in fact, your false discovery rate here, or your false discovery proportion, I really should be calling it a proportion. We'll talk about rate here later. That false discovery proportion is 495 out of 575. In other words, most of the discoveries you've made are wrong, or false. And this is super serious. If you do this in a company, like for example, a hedge fund, the game in a hedge fund is to discover little things you could bet your money on. That if some stock goes up, that means some other stock is likely to go down or whatever. Some covariance in some matrix is you believe is positive or negative. And you return, 575 discoveries that you think are worth betting on, and you bet on them. Well, here you're going to lose all your money. And in the medical domain, similarly, this is going to hurt a lot of people. Okay. And so how do you make how do you solve this? Well, first of all, you can kind of tell that just turning the type 1 error rate down or turning up the sensitivity and up the specificity, that's good, but you don't know how much it's good. Is it really getting you to where you're happy with the overall false discoveries you're making, or are you still kind of in a bad zone? And because you don't know the prevalence, you don't really know. Okay, so that's what we have to start to worry about. Okay.
Hi, Professor. I have a quick question.
Please.
So for the previous slides, the 495 false discoveries, so you said that we are achieving a very high false discovery rate because 495 is like a very high proportion out of the total discoveries that we have.
Yeah.
However, like 495 those are the false discoveries, right? Then why do we include it in the total discovery that we are having?
Okay, so in my little table, my little 2x2 table, this is a column-wise proportion. This is the right column. The right column is the times that I made a discovery. In other words, I said D equals 1, all right? The 495 is in the upper right-hand cell. It's the times where I said 1 and actually it was 0. That's a false positive. So I made 495 false positives here. That's the upper right-hand corner of the table. Now, if I go down below that, I have the lower right-hand corner of the table. That's the cases where I said D equals 1. I made a decision, I made a discovery. But there, in fact, it was the case where H equals 1. I should have made a discovery. And so I'm calling those true discoveries. There's 80 in that cell. All right, so if I look at the total in that right-hand column, I take the 495 plus the 80, and I get the total number of discoveries that I made, 575. I actually know that I made 575 discoveries because I know the discoveries I made on, and I write them down and I give them to my boss. So I know that, right? But what I don't know is which ones of those are the false discoveries and which ones are the true discoveries, because I don't know the truth. So I just give my boss the 575. And so I'm supposing that one of us knows, somehow we're a supreme being, and we actually happen to know that of all those in that right-hand column, that 495 were false and 80 were true. Okay, so if I just go back a little bit here, I think it's okay, I can do this. Right there, this is exactly that false discovery proportion that I was talking about. In 0, 1 here is 495, and in 1, 1 here is 80. And I'm taking 495 divided by the denominator, which is 575. And that's where I'm getting this number here. And I'm saying that's a terrible number. Your error is an error proportion. And your errors are almost nearly 1 as your proportion of errors. Did I answer your question?
Yes, it does. Thank you.
All right, thank you.
Hi, Professor. I had a question as well.
Please.
I was wondering, is there any particular reason when thinking of this in terms of false discovery rate instead of just looking at precision or looking at the ratio of like true positives to everything we classify as positive?
Yeah, and the reason is going to come out in the second half of the lecture here. All of these quantities are good quantities. Usually there's trade-offs, right? So if you just talk about precision, that's another name, or recall or sensitivity, specificity, just one number alone is not good, because you need to get the trade-off with some other number. If something goes up, something else is going to go down. And I'm arguing that this one is one that hasn't been kind of focused on by lots of communities nearly as much as it should. It's a very natural one. In real life, you will probably want to calculate it or know about it. And moreover, as we're about ready to learn in the second half of the lecture, this one has a very nice interpretation when we go to multiple hypotheses, and where we're not even testing the same hypothesis over and over again. We could be testing even different hypotheses, and we could have even different groups of people testing hypotheses. So this is kind of this is going to lead us into a very broad way of thinking about just bags of decisions that a decision maker makes, or even a group of decision makers. Okay, so that's kind of why I'm those are two reasons. One, I just want you to know about it because it's natural and you'll find it useful in your thinking. And secondly, as you're about to see, it allows us to get even a broader perspective on hypothesis testing when we talk about multiple testing.
All right, thank you.
All right. Our goal at this point is going to be to control errors a priori. So what I've been talking about so far is kind of like after you made a bunch of decisions, do some counts and kind of like record how well you did. These are kind of like descriptions of various fractions. And like when we think about an ROC curve, that's typically what we think about. So we take some training data and we calculate all of our false positives and negatives on the training data. We make a little plot, and it kind of tells us how well we've done after the fact. What we want to do though is have design tools that say, well, in a certain situation, here's a procedure, an algorithm, maybe a neural network, maybe a decision tree or something else, some other way of testing that we can tell you under certain assumptions is going to guaranteed to work. And so how do we turn this kind of thing into a design tool? Okay, so now we go all the way back to sort of 1930. Neyman Pearson. Neyman was the founder of the statistics department of Berkeley, a Polish mathematician who became a statistician, moved to Berkeley in the, I forget whether it's the 30s or 40s. He was certainly here by the 40s. I think it was actually in the late 30s. He was in the math department and then got tired of being in the math department. They weren't kind of giving statistics enough respect and said, I need my own department, and he eventually got it. So that was the origins of our department here. Okay, so Neyman was not a Bayesian. Neyman was very much a frequentist, as we'll talk about what that means here. But roughly speaking, it means focus on the rows of this kind of table. Okay, focus on what happens if nature is in the state 0. What do you expect to see? And then compare that with what do you expect to see if nature is in the state 1. All right, now you see something and you kind of evaluate what's the likelihood or how surprised you are given the data you've seen relative to the 0 or the 1. So it's kind of trying to go backwards without never really explicitly going backwards. Whereas the Bayesian, by inverting these conditional probabilities with Bayes' theorem, is really explicitly going backwards, and it's bringing in the prevalence to let it go backwards. Okay, so anyway, let's give Neyman Pearson their due. So they're turning the problem, they're thinking about the rows, they're thinking about the sensitivity and the specificity, the 2 rows. They called them type 1 errors and type 2. Those are 1 minus the sensitivity and 1 minus specificity. And I'm trying to avoid that language just because I kind of hope it'll die in the future. It's just too easy to forget. But anyway, they use that language. So their idea was to turn the problem of the design problem now into a constrained optimization problem. Okay, we're trying to find the best way to test. All right, and we got these 2 numbers, one of which if we make it small, the other one's going to be big, and vice versa. We have a trade-off. That's what like the ROC curve is all about. There's these trade-offs. So how do we figure out how to best manage this trade-off? Well, their idea was to take one of the 2 quantities and to constrain it to be below a certain level, and maybe they could pick 0.05 or 0.01 or some number, all right? And then subject to that, then maximize the other quantity. So if I wanted to maybe control the specificity, you know, a 1 minus specificity below some level, then I could maximize the sensitivity, you know, or vice versa. All right, so in their setup, specifically, they said, let's control the false positive probability. That's the probability of a type 1 error in their language. In other words, the probability that you make a decision of 1 when you shouldn't have. Okay, this is a false positive. Make sure that that probability, now I'm really using the probability here because this is the story before you saw data. This is the assumptions you make about the world. If nature has a certain probability distribution on data and you then make a decision based on that, there's going to be a certain probability you're going to make this error, right? And they said, well, I have to write that probability down. I have to make an assumption here. This is usually what's called a likelihood. As we talked about a minute ago, it leads to a likelihood ratio, okay? So I will draw a picture here in a minute. Hopefully you'll have, this picture will be familiar, all right? But this is the false positive probability. They said, let's keep that thing under 0.05. Let's make sure that most of the time you're not making false positive statement, false positives. Now, when I said most of the time, that's a little bit weird here. We're going to be talking about this because what do you mean most of the time? You're doing this again and again and again? And the answer is, yeah, we're doing it again and again. That's what frequentist means. We're doing it again and again and again, all right? But we're just kind of saying that every time it happens to be that h equals 0, then you only 5% of the time do you make an error, right? But what times is it going to be that h is equal to 0? All right, and they didn't talk about that because that's the prevalence, and they didn't know the prevalence, and they wanted to not assume you needed the prevalence. The Bayesians are willing to assume you need the prevalence, but not these guys. So they were just saying, okay, when h equals 0, I'm just going to make sure you don't make any errors, you know, 5%. And I don't know which times this is going to happen, but when it happens, you make no errors or 5% errors. All right, so they said, okay, given that I've constrained things in that way, now what I'm going to do is maximize the other quantity, the power. Other words, the true positive probability, also known as the sensitivity. Okay, so given that I'm not making too many false positives, I'm going to try to be as sensitive as possible. All right, and if you now write down all these probabilities, this becomes a math problem. In fact, Neyman knew about the calculus of variations, and he used the calculus of variations to solve this math problem. It's just optimize some particular integral subject to a constraint on another integral, all right? Now this picture is really the best way to think about that calculus variation problem for this level of class, but later you can learn about the fuller picture. Okay, so you've seen this picture before, but now how does it relate to what we've been talking about? Well, we have a blue curve and a red curve. The blue curve is a normal or Gaussian distribution, and it's the distribution of the data in the case where h equals 0. It's the null hypothesis. That's my blue curve there. Okay, so in other words, when the null is true, in those cases, I'm getting a spread of data, shifted over on the left. All right, now when h is equal to 1, that's my red curve. I'm getting a different Gaussian distribution. All right, and things have been shifted up to the right a little bit. Okay, so they're different, so I should have some hope of testing here. Okay, now this particular setting leads you to think that it may be a good way to design a test is to put a threshold down. So the x-axis here is some statistic, some observable quantity. You get some data, right? It's just one-dimensional data here. And so what I'm doing here is saying, if that data is bigger than some threshold, then I'm going to make a decision equals 1. I'm going to reject the null hypothesis. Okay. If I'm to the left of the threshold, then I'm going to make my decision equals 0, meaning I'm accepting the null hypothesis. Okay. So given all that setup, even though we had some continuous probabilities here, because we've thresholded, and because when we have two curves, now we've got our zeros and ones. Okay. The rows are the hypotheses. Are you the blue curve or the red curve? Okay, those are your two rows. All right. And the TN, TP, FN, FEP are exactly the four numbers in our little table. Okay, so in particular, let's suppose you're at the blue curve, meaning you're in the first row of the table. And let's suppose that you made a decision to reject. That means you were to the right of the threshold. All right. The probability that it happened is that little shaded area there, FP. Okay, and that's the upper right corner of our little table. And the area there under the curve it's a density. So that area is a probability. That's the probability being in that upper right corner. Okay. Similarly, the red shaded region is the probability that you're in the lower right corner. Okay. It's the probability of making a true positive. All right. And now hopefully you'll kind of see and remember what Neyman and Pearson said to do. They said, well, I'm going to try to make my false positives probability, that blue shaded region, smaller than some target value like 0.05. So all that means is you shift the threshold up until that area gets less than 0.05. Now you could keep shifting it further up and make that area, 0.01 or 0.001. That would meet your constraint. That would certainly be fine. In your constraint optimization problem, that's a so-called feasible solution. All right. But at the same time, you're trying to maximize your true positive probability, which is the red shaded region. So if you send the threshold off to the right too far, you're damaging your red shaded region. You're lowering the true positive probability, the sensitivity. So you don't want to do that. So you just move the threshold just enough so FP is at 0.05, and now you've maximized the red region. All right, so this is the style of argument that Neyman and Pearson did, and they did it for more general probability distributions, not just Gaussians. And they just use these likelihoods and likelihood ratios to define these kind of things, and talked about when thresholds would actually solve this problem of maximizing under a constraint. All right, so that's Neyman and Pearson in review. And in a fuller classical statistics class, of which we have a few at Berkeley, this would be kind of, quite a bit of the class would be devoted to doing this for various different distributions and talking about these numbers and so on and so forth. Okay, I'm going to argue it's not such a good idea for many of our modern problems.